Hello, welcome everybody. Today I'm going to be talking about vectors. We're going to introduce vectors into this course. So, one thing I do want to say about vectors, though, is that for a lot of you, you'll learn about it in this course and then you might never learn about it again. Calculus is probably one of the more applicable things you'll use in your future. A lot of university first year programs require a first year calculus course, which is a full year course oftentimes. Not a lot of them require vectors or linear algebra or stuff like that. However, if you are doing a mathematics background as I did, or if you're doing like a physics background or something similar to that, you may see this again, so this may be important. Even if you're not, it's still good to learn it because it'll help you get a good score in the course and will ultimately help you get scholarships or things like that for university, more offers, that sort of thing. However, I will say that a lot of you will probably learn it in this course and you may never see it again. But anyway, with that said, we're going to introduce vectors. There's actually 3 units we'll go over regarding vectors, compared to 5 we did for the calculus, just because vectors isn't quite as crucial as calculus, and there's not quite as much that we're required to cover for it. Okay, but let's talk about what is a vector. So a vector is a quantity with magnitude and direction. Okay, so for example, wind that's going 50 kilometers an hour south, right? That's a magnitude of 50 kilometers an hour, and the direction is south, it's going south. What about gravity, right? Acceleration due to gravity is 9.8 meters a second per squared. And it's going downward specifically, right? If I drop this bouncy ball, it's not going to maybe go up, maybe go down, maybe left, maybe right. It's going to go down, right? No matter what. I can do it a billion times. It's always going to go down. That's always our direction. So there we go. Now, what is a scalar? So a scalar is a quantity specifying magnitude only. Oh, I'm spelling this wrong. Quantity specifying only magnitude. Oh, that's a interesting. Only magnitude. Okay, so for example, 9.8 meters a second squared without the direction. This is just a scalar, right? What about 30 kilometers an hour? Same thing. If I don't know what direction we're going, that's just a scalar. That's not actually a vector. How about, what's another example? 30 pounds, right? That doesn't really have a direction to it. In fact, weight often doesn't, right? It's just this is how much an item or a person weighs. Okay, or how about 30 meters per second, right? Same kind of thing. We don't know which direction, right? We don't know which direction we're going with that 30 meters a second. So, yeah, so long story short, a scalar is just a quantity that we can scale something by, whereas a vector is a quantity with both magnitude and direction. Okay, so it has both those things. It specifies what direction we're going as well. So that's the key difference, and that's very important. That will come up continuously throughout this course, throughout the time that we're learning this stuff, regardless of how long that happens to be. Okay, so let's talk about a directed line segment. So it says here, draw a vector that begins at the origin and finishes at P6, 8. Well, we already kind of know how to do this. We have 6 here. Let's say 8 is up here, and the point is like that. And we just draw this. What is this? Well, this is point P. Oh, oops, I erased it. Point P. There we go. And this is my vector. We'll call the vector V, right? Vector v is the vector that begins at the origin and it ends at point P, which is 6, 8, right? You might be saying, well, I already know how to do this. I know how to plot points for 10 years, right? And that's great. The key difference here between this and what you may have done previously is we're actually showing a vector here where we have our magnitude of however long this line is, which we could figure it out using Pythagoras' theorem, and it has a certain direction, right? So a certain number of degrees, right? Now, we probably do know how to find those things, but that's not something we're used to when just making a drawing necessarily. So let's figure it out. Let's figure out what is our magnitude and what is our direction. So, first of all, how can we find our magnitude? Well, you might have guessed that we could use Pythagoras' theorem to find the magnitude. We could argue that the magnitude of the vector squared is equal to 6 squared plus 8 squared, right? Oh, and something I should specify here is that when we have these lines, like these absolute value bars, that means the magnitude of vector v, right? Vector v itself has the magnitude and the direction. When we put those lines around it, in this case, we're just talking about the magnitude specifically. So just the value of how long the line is, how long the vector is. We're not talking about the direction here. Good. So we could solve this, and actually, this is a very common triangle. You might already have this one memorized. I am not sure, but this one's going to end up being 10, I believe. So that's going to be 100. Yeah, this one's going to end up being 10. So the magnitude of our vector is 10. So that's how long the vector is, right? For lack of a better word, that's the length of the vector from O to P, which is vector v. Very good. Now, let's say we wanted to figure out the bearing of the vector. Bearing is like the direction. Well, to find that, we can also use trig ratios or other things that we already know, right? So we could say, well, in this case, we have 6 here and 8 here is this one, and it's in quadrant 1, and, we want to find out, um, you know, theta, for example. We could say, well, we know that tan theta is equal to opposite over adjacent, which is 8 over 6, or 4 over 3, whichever you'd prefer. And then we can grab a calculator. And where did I put that calculator? Yeah. Well, that's a mystery. We'll figure that out later. But anyway, you can grab a calculator, and we're going to type in 6 divided by 8, and then we're going to take the inverse of tan. So second function, and then tan is what it will be on most calculators. And then you should get 53, that theta is equal to 53.13 degrees. Or you know what, I'm just going to round it to the nearest degree and say it's about 53 degrees. Now, 53 degrees in what direction, though? We still haven't answered that. Well, let's see. It's this direction here, which is east, and then it's 53 degrees to the north, right? This direction is north. Now, we could also write this. We could also argue, well, this one, because the total is 90 degrees, would be 37 degrees. So we could also say, oh, it's north 37 degrees east. And either way is okay, unless your teacher has a certain preference. Either way is generally okay for those, so long as you do get the numbers correct and they're accurate, is the most important thing. So yeah, so for this example specifically, I'm going to say that the bearing or the direction of this vector, right, would be, or that I'll just say the total vector would be 10, and then east 53 degrees north, okay? Or another correct answer is 10, and then north 37 degrees east. And either one of those should get you full points, right? Those are good solid answers there. Okay, next let's talk about opposite and equal vectors. Okay, so for example, here, let's say I have a vector from C to A, and I have a vector from B to D, like this. These are opposite vectors, right? This, let's call it vector v. This is vector negative v. Because notice that these are exactly the same line, just one's going up and one's going down. But they're exactly the same length, and they're going in, well, the same direction, except one's going forward, one's going backward, but the same number of degrees from north, south, etc., right? Just one's going down, one's going up. So that's why one of them is the vector and one of them is the opposite vector, right? And let's think about it. Let's say I was to start here. I start in point A, and then I do the first vector, and then I do the second vector and go back. I end up right where I started. So whenever we add up opposite vectors, we just land right where we started at the end of the day, right? So that's pretty key here as well, as we just end up where we started when we add opposite vectors. Remember that that will come up on something. That will come up somewhere at some point. I can promise you that. Okay. So with that said, what about equal vectors? Let's give an example of equal vectors. Well, AB and CD are equal vectors, right? It's the exact same thing. They just start and end in different positions, but it's the exact same thing. Or what if we did A to C this way and B to D this way, right? Again, same direction, same magnitude, same everything. The only difference is starting position. But notice that for a vector to be equal to another vector, the starting positions don't have to be the same because a vector isn't even characterized by a starting position. A vector is just characterized by the fact that vectors must have a direction and a magnitude. So any vector that has the same magnitude and direction is an equal vector, right? Any vector that has the same magnitude but the opposite direction is an opposite vector. And then vectors that don't meet those criteria would be none of the above. Good. So let's write some formal definitions down here. So we have equal vectors, which are equal in magnitude and direction. Okay, so let's give some examples. Let's say AC and BD. I'm just making sure I got them in the right order and don't mix those up. Are equal vectors. Okay, so that's my first point there. My second point is that opposite vectors are equal in magnitude but have opposite direction. Okay, so for example, AB and DC, right? That's a great example of a pair of opposite vectors. And also, opposite vectors, when we add them together, we right back where we started. We get to the zero vector, which we'll talk about in a moment. So those are some key things to make sure we understand regarding the opposite and equal vectors. That it doesn't matter our starting place or our ending place. What matters is that the vector has the same magnitude and same direction. If I start at my house and I walk 5 kilometers north, and then my friend, she starts at her house, and her house is a whole different place than my house, but she walks, those are equal vectors. We did the same amount of walking in the same distance, we just had different starting points, and so those would still be equal vectors. Now let's say that we have our zero vector. So the zero vector is when the tip of the tail, so this is the zero vector, and that's when the tip and the tail are the same. So, for example, let's say I do a round trip. Let's say I drive to my school or my workplace and then I drive back home. Well, there we go. Did I move at all today? Well, technically I did, but that would still be the zero vector in terms of magnitude and direction, in terms of where I ended up at the end of the day. Yes, I went places, but I ended up in the same spot, right? Just as these vectors, if I go from C to A and then back to C again. Well, yeah, I moved, but I would still, we still end up in the same spot. So it's essentially the zero vector, right? So as long as we ended up in the same place, then zero vector. I'm going to give another example here. Let's say we have A, B, and C, and I started A and then I traveled to B, then I traveled to C, and then I traveled back to the A again. Well, in this case, let's say we have vector u plus v plus w. In this case, vector u plus vector v plus vector w is equal to the 0 vector because I ended up in the same exact spot, right? That's the reality. I ended up in the same exact spot, so 0 vector, right? So I like to think of it as places. Let's say I go to the grocery store, and then I go to the school, and then I go to the house, and then I go back to where I started. Well, I didn't really move at all. I ended up exactly where I started, even though I traveled places. So that's our 0 vector. Okay, let's talk about vectors in 2D and 3D figures. Okay, so here it's asking us to find vectors that are the same as these other vectors, okay? And keep in mind that the position in space is not important. As long as the magnitude and direction are the same, we can find equal vectors. So let's look at AB, which is the first one. AB is from here to here. Well, what else is the same as AB? Well, CD, of course. So I'm going to say that CD is my answer here. And likewise for CG, it's the same as AB. So that was a little silly of them to ask us that, but they did. Now, what about B to A? That's a different one. B to A is this one. Oh, this one going this way. So in this case, I'm going to say it's the same as DC, right? Because we're starting at B, we're going to A. And in this one, we're starting at D, going to C. Although, actually, this one, there's a few different answers because I just noticed there's these, there's these magnitude bars around here. So actually, AB has the same magnitude as BA, right? They're opposite vectors. Same with DC, and actually same with CD. So you could answer any of those, and you could be right with any of those. Because when it comes to magnitude, as long as the length is the same, then it's equal. So there's a few different answers for that one actually that are all correct. Okay, let's try this next one that's a little bit trickier. The first one it says is AB. Okay, so AB would be from here to here. Well, that's the same as DE. So I'm going to say that DE is my answer. What about the second one, CB? Okay, let's use a different color here to here. Ah, well, that's the same as F to E, right? So I'm going to say FE for this one. Then we have BE, which is from, let's see, from B all the way down to E. Well, that's the same as either CF or AD. So you could write CF or AD here, or you can write both, but do make sure you write at least one thing there, and any one of those is correct. And then here we have BC. So BC is this one on the bottom. That's the same as EF. Let's see. Oh, and here they just want the magnitude actually. So there's actually a few answers. We could write FE, or we could write EF, or we could write, actually, we don't know if it's an equilateral triangle, but we could definitely write CB, right? Would be the same magnitude. So yeah, so this one, it's just magnitude. So any of those answers is good. What about this last one, DF? So D to F. Well, the obvious answer to me is AC, so I'm just going to write that. But again, it could be CA because we're just talking about the magnitude, or it could be FD, right? Any of those is correct. They didn't really specify which one we should put, so therefore we can put any correct answer will do, basically. Okay. Well, that is everything for the introduction to vectors. Next time we'll be talking about vector addition and subtraction, so we will see you all for that. Bye, everyone.